So the Kelvin-Planck statement is it's impossible for any device that operates in a cycle to reduce or receive heat from a single source and do work. So in all those schematics, we had a sink and a source, right? We just didn't have the volcano and then our system producing energy, right? We had to reject some of the heat. It's impossible. So this is kind of, so in a couple other slides, we'll go to perpetual motion machines, where they'll show that there's not a sink and a source. So it's operating in a cycle. So so a lot of times people look at things and they determine whether they violate the second law by using the Kelvin-Planck statement. So this is just a very short version to show that the second law is certainly going to be violated because you're not removing heat and adding heat. So this is to do work, right? So an example, so I have a source which gives me QH, source at TH, and I have some system that's operating in a cycle, right? And my QL is equal to 0, and I have some work net out, and this is a violation of the Kelvin-Planck statement because it's a device that's operating in a circle where it's only receiving heat from one source and producing, and there's net work done. So this doesn't work. So QH does not equal work net out. QL cannot equal 0. And then another example is, now I have another cycle system that's working in a cycle, and I have QH equal to 0. So this is kind of my heat pump. This is more of a refrigerator, and I have QL. I have my sink or steak at TL. So in this case, QL is greater than QH because QH is equal to 0, and work net in so this is another example of something that doesn't work. So the Kelvin-Planck statement can be modified. Instead of it's not doing work, it's consuming work, but in the same general kind of terminology or concept applies. You can't just take heat from one source and not reject heat, or you can't just receive heat and not reject heat. So you have to have a sink and a source for any system to operate in a cycle. So another example of a version of the violation of the second law is when the Clausius statement, and the Clausius statement is it's impossible to construct a device that operates in a cycle to only transfer heat from a lower temperature to a lower temperature body to a higher temperature body. So in this case, there's no work net in, right? Let's just draw an example of that. Source at TH, sink at TL. I have my system that's operating in a cycle, and I have my QL and my QH, and in this case my work net in is equal to 0. So here I've constructed a device that transfers heat from a lower temperature body from my stake to my source without any energy input other than that. So this would be, if you made such a device, we'd never have to worry about, we won't need air conditioners, right? Because we won't need a traditional air conditioner because our house would just stay cool, right? We wouldn't need to plug them into the electric grid. We'd have this device that would just cool our house and reject to Florida summer, right? So only you have to have some network in order for a refrigerator to work. And the reason for that is QH has to be greater than QL. So if we could find a way to make QL greater than QH, then this would work. But this doesn't happen. QH always has to be greater than QL. Trying to think of an entropy reason as to why. So you remember the TDS statement, the TDS question? So we can relate QH to delta S, right? TDS, right? Q, TDS question. Q is equal to TDS, right? So here I would have a delta S associated with this, and here I would have a delta S associated with this. And so if QH, so let's just draw. So Q is equal to TDS. So if I have QH and TH, so if I divide my QH by TH, I have a delta S. And if I were to do the same thing here, QL over TL, there would be a difference in delta F and in the change in entropy. And so from this example of the second law, you can show that QH has to be greater than QL because TL is less than. Right? Because my delta S on both sides has to be equal. Otherwise, it can't be working in a cycle because then my system would be constantly increasing in entropy. And at some point, right, its entropy would increase and increase and increase and increase and increase, and then what? Maybe that's not the best example. I just thought of it just a second ago. But anyways, okay. So work net in has to be greater than 0, right? Not greater than equal to 0, greater than 0. This must hold. So this is a shorthand version of the Clausius statement that in order for a refrigerator to work, you have to put work in. And still QL must be less than QH. This must hold too. Or work must be done on the system by an external source. So just some basic definitions. A reversible process is a process that can be reversed without leaving, any effect on the surroundings. So what would be, so
wouldn't anything have some heat loss? So wouldn't that always affect the surroundings?
yeah, so this is kind of a hypothetical, right? Reversible process is more or less hypothetical. In principle, it can happen, right? You can have only reversible heat. So let's just say I want to use a balloon, right? But maybe that's not the best one. So if there's a balloon, well, that's not it. I'm trying to think of some way, but so we used that circuit example earlier on where we had a circuit, and we had a battery, and then the battery got current running through it, which generated heat, which heated the gas surrounding it. So in that case, I made it isolated, and I drew a box around it. And so the heat from the circuit went to the gas, and of course the gas couldn't talk about the surroundings, but in this case the gas was the surroundings, and it heated the gas. So if all that heat that went to the gas was reversible, then when the gas could give back heat to the circuit and recharge the battery. But of course, there's no such thing as that. Well, of course, if we had it in a certain way, there's no way to make the heat charge a battery like that. But nevertheless, it's the fact that if I could give heat to the gas and the gas could give equal heat back, so it was all reversible heat, then if I asked every gas molecule, they wouldn't know that they would just receive heat and gave it away. They'd be at the exact same state they were before. All their vibrational modes would be the same. So if I give heat to something and then it gives it back to me in an equal amount, it's going to still be at its same temperature and pressure, and it has no memory of the exchange of heat. So reversible process means that whenever I give any type of energy, not just heat, it can give back equal amount, and it's going to be at the exact same vibrational state, mode, temperature, pressure, whatever it is. There's no trace on the surrounding.
Isn't that kind of like what you were saying at the top of the page, where that's not possible?
It's not possible. In principle, it is. You can devise a system that is reversible, that after it goes to one state and back again, the surroundings don't know. There's no trace. It didn't know that it went from one state to the next. All it knows is the state it's at now, and it's identical to what it was before. So in principle, it's possible. In practice, it's impossible. Because you always have some trace on the surroundings, right? So if I give heat to a gas, and then it gives it all back to me, it was all those molecules were vibrating in some way. To get them all vibrating the exact same way they were before, I guess in principle it's possible, but in likelihood it's not. They're going to be changed a little bit. So irreversible process is any process that, when reversed, has an effect on its surroundings. So, me moving in this room, right? I can go from this state to this state and then come back again. The reality is, even though I come back and forth, I move the air molecules around. The air molecules know that I moved, right? So, if I add heat to a gas and then subtract the same amount of heat back, the gas is always going to know that heat was, even if I remove the exact amount of heat from it, the gas is going to know that heat was removed because it's going to be vibrating a little bit differently. I'm going to change the distribution of velocities, right, in the gas. It might be still at that same average temperature and pressure after, but it's going to know that something happened. And this is what happens in practice for any type of system or device you make. And the goal as an engineer is to make it as irreversible as possible, because when you're making it as reversible as possible, because when you make it as reversible as possible, you minimize the amount of irreversible heat, which means you minimize the effect on the surroundings. So the last thing I want to do related to this is go over some examples of perpetual motion machines. So these are in the back of the book, or in chapter 6. So here's an example of a perpetual motion machine where I have a pump. You can see I have no work input to the pump. The pump is pumping, right? And the turbine is actually turning the pump. So my boundary, there's no external work input to this. But I have some work output. So boiler, resistive heater, right? So I take in some liquid, high pressure liquid, still in the liquid state. I create it into a superheated vapor or a higher energy, right, liquid, which then goes to the turbine. The turbine takes that higher energy fluid and reduces this energy fluid and gets a work output. So some of that work output from the turbine goes to the generator and goes to the pump, powers the pump. So the generator then creates electric power, which then puts resistive heater through the boiler, and then the condenser just rejects out to my lake. And so I have this thing which gives me a network output by only rejecting heat to my low temperature source or sink. So this is a violation of what statement?
There's no work in.
What's that?
There's no work in.
So it's a violation of the Kelvin Planck statement. You can have work out, right? So if this is net work out, but there's no work in, so I guess it's a violation of both statements. But in general, I need some heat from a high temperature source, right? So I need some heat input. And so what laws does it violate? Does it violate the first law? If I do energy balance on this, it does? So let's just write it out. So all my forms of energy in are 0, right? So there's no heat, work, energy in is equal to 0 minus energy out. So what are my forms of energy out?
Q out and work out.
Yep, Q out plus work out, and it's net, right? So whatever. So I have that equals delta U. Okay, I can put dots above this, right? Because I have a cycle system. So let's just put dots above it. So whatever, it's 0. So I have Q out, network, power out. And then I'm operating in a cycle, whether I just make it one cycle and have a delta U or have it working at steady state, this is equal to 0. So does this violate the first law?
Yeah.
Do I have balance?
No.
So minus, so minus Q out equals workout net. So I guess it would mean that this has to be Qn in order for it to be right? So I guess it does violate, right? Because I've defined that as Q out. So in this respect, well then it would say that this needs to be Qn. But then if this is Qn, because minus Q out is equivalent to Qn, so Qn equals workout. So yes and no, it violates the first law. So we just defined this wrong. So I guess it violates the first law, right? Because there's not balance. So yes. How about the second law? Does it violate the second law?
Yeah, 'cause
So we know we can use those Kelvin-Planck statements to say, oh yeah, it violates the second law, right? And that's not really, that's a good thing to do as an engineer, right? To know those statements to see if it violates the second law. But there's another way we can do this. So we automatically know that it violates the Kelvin-Planck statement, right? Because it needs to take heat and remove heat to two different things. You can't just do work by only rejecting heat or receiving heat, right? You have to reject and receive heat to do work. So it's yes. I'm going to get to this in a second. How about the third law? Does it violate the third law?
No, since that just has to do with
We can't.
P approaching zero as it approaches absolute.
Yeah, so it's hard to do because this isn't a homogeneous system in complete internal equilibrium. So we can't really say whether it violates the third law because this is a multi-component system, right? Not in complete internal equilibrium, so it's really hard to justify. So say not homogeneous. So now related to the second law. So another thing we can do is we can do what is called entropy balance, and this is the last slides on chapter 6. So I'm transitioning into chapter 7 here, and so what I'm going to write down is entropy balance, which is the foundation of seeing if something violates the second law. So just like we had energy balance where energy in minus energy out equals the change in internal energy in my system, right? And I can put it in rate form. I'm going to have something similar where I'm going to have entropy in minus entropy out plus entropy generated equals delta S system. Okay? Now, what I'm going to get to in more detail later on is, remember how energy in can be in the form of heat, work, and mass? Now, entropy in has a contribution due to heat, which I can write real quick with the tedious question. So you can see right away that entropy is coupled with heat, right? So entropy has a heat and a mass contribution, but no work contribution. And just like entropy out has a heat and mass, no work. So with energy in, I had heat, mass, and work forms of energy, right? And entropy, I can have an entropy contribution due to heat and an entropy contribution due to mass, but there's no entropy contribution due to work. Work is external. Work changes the heat and mass, but there's no form of entropy associated with work. So in regards to this picture here, I have entropy in of what? So let's put dots above it. So what heat or mass do I add to my system? No heat, no mass, right? So my rate of entropy due to heat and mass coming in is 0. I'm just going to write up here heat and mass. Okay? And so this is 0. And then my entropy out, all I have as an output is Q dot out. And then using this, Q dot out over TB, where this is my boundary temperature. So I have a minus Q dot out. So my entropy associated with the heat leaving, just straight from, so I have a minus. And then there's no mass leaving. So it's that plus S gen dot equals what? So this is a perpetual motion machine, so it's supposed to be working at steady state. So what is this?
0.
0, right? It's working at steady state. It's a perpetual motion machine or a perpetual work producing machine. All I do is get the fluid moving, which then heats it, runs it, generates power, and then provides some of the power out to keep it moving, and I'm constantly providing work out, right? So it's a perpetual work production, right? Power output machine. And it's working at steady state for it to be. And so just like in energy balance, when something's working at steady state, my delta U dot is equal to 0 at steady state. The same applies during entropy balance. So then I have S gen dot equals such. But from energy balance, we saw that this has to be actually Qn. So this is a negative value when we did this. So let me just write it out. So S gen dot equals Q out over TV dot, but then this is actually not true. It's actually minus, or it's, what's that? So from here, right, is work net out, so I have minus work out dot over TV. I wish I would have. There's a dot above that. So my rate of entropy generation is a negative quantity. And so this thing, just like how we wrote the second law where delta S has to be greater than or equal to 0. So this has to be, whether it's S gen dot or S gen, this has to be greater than or equal to 0. So we can see by combining energy balance with entropy balance that this is a violation of the second law. Now, of course, I jumped way ahead and I introduced this whole idea of entropy balance. Okay. But this is what you're gonna be tested on throughout the second exam and the final more than anything. So we'll be working on it the rest of the semester, these concepts. But this is just here I just brought, we can use the Kelvin-Planck statement, right, or the Clausius statement to show that it's a violation of the second law. We can use the first law or energy balance to show it's a violation there, show this thing doesn't work. Or we can go through a full entropy balance coupled with energy balance. Of course, we didn't even need to do this after here, but we might have had a scenario where it wasn't violated for energy balance, and then once we do this, we find out it was. But then we apply this, and then we get a relationship. Okay, so the last example. So now I have this work producing device, and I have Qn, and now the pump is just pumping. I don't know how. There's no power from the turbine to the pump, and it's coming through, and it's saying I constantly have work output. So I could have Qn. So when I do this, I have the same equations as I had before for this, but now I have Qn equals work net out. So if I do energy balance, I'm going to end up getting Qn dot equals work out net. So this example here, I just did energy balances. It doesn't violate the first law. So it doesn't violate the first law. I'm adding heat and I'm getting work out, equal amount of work out relative to the heat I add. So it doesn't violate. So no. Does it violate the second law? Well, I can use the Kelvin-Planck statement and show and quickly identify that I'm getting work done by only taking heat from a single source. So just from the statement, I can say yes, it violates the second law. Or I could go through an entropy balance and show. And so let's just do the entropy balance, right? So yes, Kelvin-Planck statement. So how about entropy balance? So let's do it. S in dot minus S out dot plus S gen dot equals delta S dot, and I'm working in a cycle, right, at steady state. So we're going to say that this is 0, and S in, I only have one form of S in, right, and that's due to heat. So then I got Qn dot over some boundary temperature, TB. I have no entropy out, so this is equal to minus S gen dot, or I can turn it around, minus Qn, right? So that means minus work out over TB from there. But nevertheless, I have a negative, I have S gen equals a negative. So again, I have, by doing energy balance, I can quickly see, I can use the Kelvin-Planck statement, or I can go through a full entropy balance, and then I find that this S gen dot, the rate of entropy generated by my process, is a negative number. So I'm actually decreasing entropy as it works. So in principle, this thing goes to entropy at absolute 0. So in some ways, this device will bring my system to absolute 0 by adding heat, right? Because the entropy only approaches 0 at absolute 0, right? The net entropy. So this system not only violates the second law, it says that by adding heat to a system that produces work out, I'm going to bring it to absolute 0. Okay, I think it's interesting, but anyways, okay. Let me just write this out the better way. So S gen dot equals minus Qn dot over TB, which then implies S gen dot equals minus work out dot over TB. So we already know that the work out was defined to be a positive value. Of course, temperature is a positive, right, number. So my S gen is a negative quantity. My rate of entropy generated is actually, so that means I'm decreasing the entropy. So yes, through entropy balance, third law, cannot